Okay, let's finish up the discussion here about question 2. We had just finished in the previous video 2b, which is a fairly difficult problem here, where you have to calculate all of the values of g at -4, +1, +5, and +7 using the fundamental theorem of calculus and integration and calculating geometrically the area under this graph. All right, so moving on, 2c says the function h, so now they're introducing a new function, capital H, is defined as 3x minus the area under f of t dt. So they did a little variable change here, but they're really just employing the fundamental theorem of calculus here because they ask us to find h prime and h double prime at -1. So we're taking this equation and just differentiating it. The derivative of h is the derivative of each piece. So the derivative of 3x is 3, and then the derivative here is the fundamental theorem of calculus, part 1, as we discussed in the course. Your upper bound is 2x. You know what? I'm going to go through this because I think this is something that is too often forgotten. So I'm going to say, if I wanted to integrate f of t dt, actually, if I want to take the derivative, let's say it this way. If I wanted to integrate it, I would have to find, let's say we found capital F. I'd have to find capital F, if I was integrating this, capital F at the upper bound 2x, all right, minus capital F at the lower bound 1. But I am differentiating, so I integrated, and then I would have to take the derivative of that integral, all right? And the derivative of the integral would make this disappear, but then the derivative of f, capital F, gets me back to little f. So I get little f of 2x, but this derivative requires the chain rule, so times another 2. All right, so in other words, differentiating this integral means taking 2x and plugging in for t, like I did here, and then multiplying by the derivative of that 2x. I gave you guys this formula in the notes, and this is a nice little trick that that I think students tend to overlook too frequently. But again, as I just explained, I could integrate, which I did here between these brackets, and I just called the antiderivative capital F, but I could integrate using the fundamental theorem of calculus part 2 and then differentiate again, and I get right back to this, which is why that's what I have right here. All right, so there's my h prime. In a moment over here to the right, you can see that I find h prime of -1. But I went ahead and moved on here. H double prime is the derivative of h prime. So the derivative of the 3 is 0, that goes away. And then I have to differentiate this. Well, this is a chain rule, 2x inside. So f prime of 2x, but then I have to multiply by another 2, which is the derivative of that 2x. So I end up with -4 f prime 2x as my second derivative. So first derivative, second derivative given. Now I go on and I put -1 in. If I put -1 into this, it's 3 minus 2 times f of -2. The -1 changes that. And of course, f of -2, I can pull straight off the graph. F of -2 is -1 right here, if you look up here at the graph. -2, -1. All right? So 3 plus 2 is 5. This one you would have to go all the way to this value. You can't just leave it as f of -2. What you could do is you could replace this -2 with -1 and leave it as 3 minus 2 times -1, and that'd be fine. But I don't see why you would do that. It's simple enough to just go to 5. And then here I plug in -1 into this formula, -4 f prime 2x, and I get -4 f prime of -2. Again, we said -2 was -1, so I put I'm sorry, no, back up. This is f prime of -2, and f prime requires I look at the slope of the graph at -2. So the slope here at x equal -2 is on this line, is the slope of this line. And the slope of this line is -1/2. You go down to, go down 2 and over 4, so -1/2. So -4 times -1/2 gives me +2. So the answers are 5 and 2. All right. 1 point for the chain rule on either h prime or h double prime. So you could make a mistake on one of these and still get a point for showing chain rule. And then you get 1 point for each of the given answers, 5 and 2. Okay? Let's move on to D. In part D, we are given yet another function that relates and ties back to f in some way. But the function k is defined as a piecewise function which involves f of x, surrounding the value of x equals 0. It says, is the function k continuous at 0? Why or why not? Well, this is a 2-point question. Continuity is just a matter of really proving this statement here. If this statement is true, then it's continuous. So we have to prove that the limit exists, and we have to prove that the limit equals the same value as the function at x equals 0. So to prove the limit exists, we have to do left-hand limit and the right-hand limit. All right, this here is the left-hand limit. That means I use this piece, and it's the limit as x approaches 0 of k, so I put 0 in, direct substitution, put 0 in for x, and really I'm just evaluating, again, that 0 goes away, and 3 minus 0 is f of 3, so I'm just evaluating f of 3. So I go back to the table, and f of 3 is -2, right? The second piece is just f of x. So on the right side, this is where x is greater than 0. So the limit as x approaches 0 from the right is equal to f of 0, which we just, actually we just go back up to the graph, or go back up to the table here. F of 0 is also -2. So we have -2 for the left and -2 for the right, which means the limit exists and is equal to, I'm going to write it out here. Therefore, the limit as x approaches 0 of k of x exists and is equal to -2. All right? If both the left and the right are equal. All right, then we have to prove that k of 0. This statement here is what many students tend to leave out of these problems. You have to show that k of 0 equals -2, or at least make that statement somewhere. You don't necessarily have to show it, but that has to be included in the statement. So k of 0 clearly is going to do the same math that we did up here on the left-hand limit, and you end up with -2. So yes, k is continuous at 0 because k of 0 is equal to the limit as x approaches 0, and they both equal -2. You don't have to make this statement again, but I did. All right, 2 points. One for showing both the left and right-hand limit. If either one of those is wrong, you'll miss that point, and then one for the conclusion. Clearly, if you get this wrong, you're likely to get this wrong, and you would get 0 points on this problem. All right, moving on. Part E, the last part of this exam. We're told now that this function f represents the velocity of some particle moving along a horizontal line or a horizontal axis. So between 0 and 7. The velocity v of a particle is modeled by the equation v of t equals f of t. Find the acceleration, which is the derivative of velocity, at 1/2. Then we're asked, is the speed of the particle increasing, decreasing, or neither at that value of 1/2? And give a reason for your answer. Okay, so acceleration is the derivative of velocity. The derivative of velocity, if velocity is defined as f of t, would be f prime of t. So a of 1/2, which is what they ask for, the acceleration at time 1/2, would have to be f prime of 1/2. So the derivative on f at 1/2 is clearly the slope of this line right here. So up 2 over 1, the slope is 2. So the acceleration at 1/2 is +2. All right, so we've answered the first part That's 1 point. Very, very simple, I think. Just look at the slope of the line at 1/2. The second part is more of a concept, clearly. V of 1/2, which is of course the same, this is the velocity, which is of course the same as the function at 1/2. Function value at 1/2, it appears to be -1. We don't know if it's exactly -1 or not, but we do know it's negative because it's below the x-axis. So f of 1/2 is a negative number. So the acceleration here is positive, while the velocity is negative. So that's like saying you are pressing the gas pedal while moving forward. So like you're in a car and while moving backwards. So you're in a car, you're moving backwards, like you're rolling down a hill. That would be negative velocity. You're moving backwards, right? Because remember, velocity is a directed motion, directed rate of change. So we're moving backwards. If our velocity is negative, we're moving backwards. So let's say you're walking backwards. You're walking backwards or running backwards, and then all of a sudden somebody pushes you from the back. While you're walking backwards, somebody pushes you. That's going to slow you down. Or you're moving backwards in a car and you press the gas pedal. You're not in reverse, you're just rolling, and you press the gas pedal to try to move you forward. All of a sudden, your backward motion slows so that you can turn and go forward. Or if you're walking backwards, again, velocity is negative, you're walking backwards, and somebody pushes you from the back, that's a positive acceleration, that push is a positive acceleration, then you're going to slow down from walking backwards. Your speed is decreasing. I'm trying to give you, without having the ability to literally have somebody standing or show a demonstration, I'm trying to give you this explanation, but really the easy way to remember this is that speed will increase when velocity and acceleration have the same sign. If you're pushing yourself in the same direction you're already moving, all right? If you're moving backwards and you press the gas pedal while you're moving backwards, if you press the gas pedal while you're in reverse, then you're going to speed up in reverse. If you're moving forward and you press the gas pedal while in a drive, you're going to go forward. That's a acceleration. That's, again, speed and acceleration are the same sign. But if they're different signs, if speed and acceleration have opposite signs, in this case, acceleration is positive while velocity is negative, then you're going to slow down. All right, so there's our explanation. Okay, there it is. This mock exam was pretty good. A lot of good things going on in it, and it covers, man, a lot of concepts in total. Some major concepts in there. Mean value theorem. There are plenty of theorems that were not covered in this test, but mean value theorem, fundamental theorem of calculus, what we call rectilinear motion with this last problem. We've got continuity covered in this problem D. We had chain rule covered in this problem C, covered in great detail with fundamental theorem of calculus a little bit as well. More fundamental theorem of calculus in problem B here. I'm going back through with a quick review. This was a relationship between between function, a derivative, and a second derivative for points of inflection. Going up here, this was a massive question dealing with separation of variables and differential equations. Big topics, 6 points. This was a 35-point free response set. Question 1 and question 2 altogether was 35 points. This was 6 of them. That's a huge amount. All right, 1/6 of the test for that one question, really. A little more than 1/6. This question here was a quotient rule problem. Straight up, just can you operate and show the quotient rule? This was a L'Hopital's rule question, which also included a little bit of chain rule stuff, I think. So L'Hopital's rule with chain rule. This was a U substitution. Can you integrate using U substitution? A little bit of a tough U substitution, not necessarily the actual part of U substitution, but being able to understand conceptually that you even had to do a U substitution was hard on this question. This one here, fundamental concepts surrounding what an integral represents, the area under the curve, right? So Riemann sums, approximating area under a curve. That's what this question was talking about. And then this 1A was a mean value theorem problem. Major topics in calculus all represented in this test. All right, reach out if you got questions.